Okay, hi everyone. In this video, I'm going to sort of summarize these three ideas that we are, or three or four ideas that we're trying to connect to each other. Okay, so the first idea is to understand what the antiderivative represents. So what we found is this. We found that if I take a function f of x, looks like that, and let's suppose I call these points x0, x1, x2, x3, and x4. Then what capital F of x does is it gives you another function, right? And at exactly these points, x0, x1, x2, x3, and x4, it has certain values. What those values are is the cumulative area. So at x0, it's how much area is under the curve here, right? So it's 0. So this is cumulative area. At x1, what is the area? That's this part. So whatever that value is, that's going to be the value at x1. At x2, it's this cumulative area, so it's this whole, which means it is always increasing, so it's something larger, something here. When you go to x3 now it's all of this area. So that gives you some other value. And then at x4, it gives you just another value. But all of these are increasing. So it'll give you some curve, but this curve is it's giving you the cumulative area. Okay. But now, if I look at what these values represent, right? So f of x1, right? What it represents is this area, which is in cyan, right? So let's suppose I label these areas. This represents A1, A2, A3, and A4. Then f of x1, what it really represents is the area A1. F of x2 represents A1 plus A2. And f of x3 represents A1 plus A2 plus A3. And f of x4 represents A1 plus A2 plus A3 plus A4. Okay, so it's the total area. So from here, I get this relation that f of x1 minus f of x0 is A1, which is just the first strip. F of x2 minus f of x1 is A2. That's just the second individual strip. Capital F of x3 minus f of x2 is the third individual strip, and capital F of x4 minus x3 is the fourth individual strip. And if I add them up, these capital F's kind of cancel each other out, and I get f of x4 minus f of x0 is the sum of all of these. Okay, which is kind of nice, because what it's telling me is that if I have the antiderivative function and I find its value at the end point and the beginning point, and I look at the difference, this difference is basically the area under the curve. That's the first idea. The second idea we said is, what is another way in which we can estimate area? Okay, so we see that antiderivative estimates area. The other way in which we can estimate an area is, again, we have x0, x1, x2, x3, and suppose x4. The other way is that we break this into rectangles. One of the ways of breaking this into rectangles is going to be this, 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 and this. And we estimate this area, and we estimate the sum of these areas and see what that comes out to. Now it turns out that if I make this length fixed, right? If I make all of these delta x's, then the area basically comes out to delta x times f of, so it's going to be these heights. That's f of x1 plus f of x2 plus f of x3 plus f of x4. And in fact, if we make n rectangles, then the area is going to be limit of f of x naught plus dot 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 f of xn. No, sorry, f of x1 dot 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 f of xn. So we're saying that if we make the rectangles skinnier and skinnier, then they are going to give us a better estimate of the area. So at this point, what we have is we have two different interpretations of areas. We have an interpretation of area based on difference of cumulative areas, which is from the antiderivative, and the second one is using an estimation method using rectangles. Now since the area must be the same, right? Area must be the same, we can equate them. And when we do so, we give the antiderivative a new name. Okay, we call it an integral. So here's the definition. So let's see what the definition says. It says, if f is a function which is defined for x between a and b, we take that interval and we divide it into n subintervals of equal width, b minus a over n. We let x0 be the starting point, and then we have this bunch of other points, and we let x1 star, x2 star, xn star be sample points. Then the limit as n goes to infinity of the sum of all the rectangles, areas. These are areas of rectangles, right? Think about it. That's f of x1 star for each sample represents the height of the rectangle, and delta x is the width. And we take this sum from 1 to n, right? This should equal our antiderivative. And the way we use it is using this symbol, which says it should equal. So how is this read? We read this as integral of f of x from a to b. And what this really is capital F of b minus capital F of a. So what is capital F? Capital F is the antiderivative, and b and a are the endpoints. This is basically what we have over here. The sum of rectangles equals f of x4 minus capital F of x0. Now since we have, so far we were using this small f and capital F notation, it's not very efficient. And since we already have like a prime and a d over dx notation for derivative, it makes sense to have own notation for antiderivative. But we don't want to call it antiderivative because they are slightly different things. So instead we use the word definite integral, and that's what we're going to call it. So definite integral, basically it is the difference of the antiderivatives at the endpoints, but it can also be thought of as, that's why you get the name integral, is because you're integrating these small rectangles, these small pieces to get the whole thing. Okay, so it's actually an infinite summation. So integral is an integral is an infinite summation of infinitely small things, right? Because as you increase n, these rectangles are becoming thinner and thinner. And by becoming thinner and thinner, their areas are becoming almost zero. But by adding all these things which are almost zero, you end up getting something which is non-zero, right? You get the whole area. So that's called integration. Okay. Now, this sort of also relieves us of the plus c business that we had with the antiderivative, because by making it concrete, that we are looking at the area under this curve, we fix the value of c automatically. We'll look at some examples later on to see how that works. Let's look at one example in this video before I end this video. Is example, let's say, evaluate the sum of areas for the function, let's say x cubed minus 6x with a0, b3, and n6, and then verify by evaluating the integral. So 0 to 3 x cubed minus 6x dx. Okay, so let's do the first part. The first part says I have a, I have b, I have n. So I can find delta x, which is the width. That's going to be the length of the interval over n, that is 0.5. Which means I have my points now. My x0 is 0, my x1 is 0.5, my x2 is 1, then I have 1.5, then I have 2, and I have 2.5, and I have 3. Now also suppose that it says take right endpoints, okay, which means I'm taking these points. When you take the right endpoint, you skip the first point being 0. Okay. Okay, now we need to evaluate the function values at each of these points, right? So what is the sum? The sum, or the area, is going to be delta x, f of x1, f of x2, so on till f of x6. Delta x is 0.5, and this is going to be what? 1 cube minus 6. Sorry, x1 is 0.5. So it's going to be 0.5 cube minus 6 times 0.5 plus 1 cube minus 6 times 1 plus dot 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 3 cube minus 6 times 3, so on. And if you evaluate this, this is going to come out to be negative 3.9375. Okay. Now, this is coming out to be negative, which by our interpretation of area is kind of troublesome, but it's still okay because we can interpret negative, it being negative, by saying that it is below the x-axis. Okay, now let's see how we can evaluate it by using the integral. Okay, so if we can get the same value, now what does this symbol say? This symbol is saying this is my f. So what should my capital F be? That's my antiderivative. The antiderivative of x cubed is x to the 4 over 4. And the antiderivative of 6x is 6x squared over 2. So we write the antiderivative, and then we still need the endpoints, so we put a vertical line with the endpoints 0 to 3. And then we plug in those values. So this becomes 3 to the power 4 over 4 minus 6 over 2, 3 squared minus 0 to the 4 over 4 minus 6 0 squared over 2. So this is going to be 81 over 4 minus 54 over 2 minus 0, and this comes out to 4. 81 minus 108, which is 27, negative 27 over 4. Is that correct? 19, yeah, negative 27 over 4. So maybe this is not a very good estimate then, right? Because it's about negative 4, where this is about negative 6. But that makes sense because we only used 6 rectangles here. If we used more rectangles, it would have been a much closer value. Okay. So this is one way of evaluating the sum of areas and then verifying it by evaluating the antiderivative. Okay. So I'm going to end this video here, and then we are going to look at some more examples.